Hello. In this module, we are going to make a connection between entropy and the second law of thermodynamics, and then develop the entropy balance equation in the same format as mass and energy balance equations that we have done in the previous module. So let's begin by drawing a very generic system. Well, I'll draw a simple system, but you can use your imagination to make it more complicated. So let's say we have an inlet state I and exit state E of an open generic system. And let's say we have some shaft work transfer. Let's say pedal wheel is turning. And also let's say that heat is being transferred here into the system. Let's do a system boundary. Okay, so we want to develop the entropy balance equation for this system. Simple thing first. We understand as mass goes in, it carries entropy with it. So entropy transport S dot would be simply just m dot S, just like if you recall that flow energy transport is given by equations such as this. These are called transport equations. So as mass goes in, it will carry entropy in. As mass comes out, it will transport entropy out. So we have entropy going in at the inlet location would be m dot times Si, m dot I times Si, and here m dot E times Se. Well, to understand what will happen because of the work and heat transfer to entropy, we have to go back to the definition of entropy. If you recall what entropy is given for a big system, K times ln omega, where omega is the number of ways in which the internal energy of a system can be distributed amongst its molecules. So it sounds like a very abstruse, abstract concept. So let's try to simplify the idea and see if we can get an intuitive understanding of what happens. So essentially, entropy is a measure of in how many ways energy can be stored. So it's a kind of a measure of the disorganization inside the system. So let's say, and we also recall from our fundamental understanding that the internal energy is distributed amongst its molecules, molecule being the smallest unit of a system. So each molecule in our model, if you recall, will have a ladder of energy levels. And we also know if the temperature of a system is higher, of course the molecule will have more energy, but it will also have more levels of energy. And that's also intuitively understandable. If the temperature is higher, more doors are open to a molecule. If temperature is really, really high, even electrons can start jumping from one orbit to another, opening up even more ways to store energy. Of course, we know that as temperature increases, temperature being a measure of the kinetic energy of the molecules, its kinetic energy increases. But it is nice to have a picture in your mind that the higher the temperature, let's say this is a system at 1000 Kelvin, and this is a system at 500 Kelvin. So here, maybe the molecules can be stored, let's say, I'm just taking an arbitrary number. I'm sorry, this would be 1000 Kelvin. And this is our 500 Kelvin case. Just suppose here the energy can be stored in 10 ways. Then here, probably the energy can be stored in 50 ways, 50 different levels. Okay, so we'll keep this model in our mind, but let's try to understand what happens when heat crosses the boundary. When heat is crossing a boundary by conduction, well, you don't have to know exactly how the heat transfer happens, but in general, there is always molecule to molecule transfer. So the molecules on the red boundary is having higher kinetic energy than the molecule inside. As a result, these molecules which are more energetic are passing on energy into the molecules inside the systems. So, of course, if there is more heat is transferred as the molecule is passing energy from one molecule to another, and it also passes its own different energy levels. In other words, heat transfer always carries entropy with it. What is even more difficult to understand is that the amount of entropy transfer is proportional to heat transfer, but it is moderated by the temperature of the boundary. In other words, if the boundary temperature is very high, the entropy transfer is a little bit less. Look at this relationship, inverse relationship. That's kind of a little bit difficult to understand. One will think that if the temperature is higher, aren't molecules having more number of waves, how in the world the entropy transfer is decreasing in that case? Well, think about it. When the temperature is really, really high, suppose this is the boundary molecules, then look at what happens. Most of the energy levels are so concentrated, these are not uniformly distributed. As temperature is higher, the higher energy levels are very close to each other. So most of the molecules at high temperature will probably be in this zone. As a result, because of entropy transfer, the energy levels we are talking about, they don't have so much variation. Whereas the boundary temperature is lower, suppose the boundary temperature is 500 Kelvin, then probably the molecules will be over a bigger range. And as a result, because the energy levels are more sparse in this case, so therefore, the variation introduced, the number of ways in which you can store things, the variation introduced will be higher at lower temperature. Well, it's more complicated than that. Derivation of this is quite complicated through quantum mechanics, but there are other ways in which you can get to that principle. But we will just axiomatically mention that whenever there is a heat transfer, it carries entropy. So if heat enters the system, not only energy has entered the system, there are more number of ways in which energy can be stored has entered the system. Now there are more chairs in the room, think like that. So there will be more ways in which energy can be stored. On the other hand, when work crosses boundary, let's say in this case the shaft work, all the molecules of the shaft are moving the same way. There is no randomness, there is no levels associated with it. So therefore, when external work such as shaft work, electrical work, or boundary work crosses the boundary, there is no entropy transfer. So W dot external does not carry entropy. Why? Entropy is a measure of disorganization as given by ln omega, logarithm of the number of ways in which energy can be stored, and external work being all about organized energy. When a baseball, suppose a baseball is moving at a constant speed, all the molecules are moving at that speed. These are organized kinetic energy, the organized kinetic energy of the molecules, as opposed to U, which is composed of the disorganized kinetic energy of molecules, disorganized potential energy of molecules. So when there is external work, say the shaft work, in which case all the molecules of the shaft moves the same way, electrical work, in which case all the electrons moves the same way, boundary work, suppose a piston is moving down, all the molecules at the boundary are moving at the same way. There is no entropy transfer. On the other hand, during heat transfer, there is all this randomness involved. You don't know which energy level is going to be activated when some heat is transferred. So suppose a hot gas, suppose you touch a hot plate, then the hot plate is not only going to transfer heat to your finger, it is going to bombard your neurons here with different kind of energy levels. As a result, your body will get entropy from this hot surface. How? Because different energy levels are hitting your molecules on your fingertip. As a result, all these molecules will be activated at different levels, increasing the number of ways in which energy is stored. And so all you need to know in this case is the boundary temperature at which the heat is crossing the boundary, And this will be our measure of how much entropy is crossing the boundary. So taking a look at this system again, entropy can be coming in with mass. That's simple to understand. Any lump of fluid will carry energy, entropy, kinetic energy. This is called transport. Entropy can also come in because of heat, and the amount will be q dot by TB per second. And no entropy crosses because of external work. Now there is only one more way in which entropy can be affected in a system, and that's quite important. The way in which entropy can be affected is called entropy generation, and that's quite important to have a handle on. And that's what is connected with the second law of thermodynamics. So let's understand what is the entropy generation rate, S dot gen. Well, that's what makes entropy so important, because there are natural phenomena where you will find a difference get destroyed. I give you a simple example. Suppose here is two identical blocks of metal. One is at 1000 Kelvin and one is at 500 Kelvin. And the whole system is insulated. In other words, there is no external heat transfer, so no entropy is coming in or going out, no mass transfer. So we all know that after some time, after a long time, these two blocks the temperature will equilibrate, and let's say both become 750 Kelvin. We know fundamentally this is what happens. Even without any idea of energy equation, we know that hot and cold, when they're together, heat will flow, and ultimately the difference will get destroyed. We not only see it in temperature difference, we see that in many other difference destroying natural phenomena. For instance, if we drop a drop of ink in clear water, you'll see the concentration difference being destroyed. If you, for instance, have a voltage difference, a current will flow until the voltage difference gets destroyed. If you have a velocity difference, you'll find nature will try to destroy the velocity difference. It will invent a mechanism called friction, which will oppose the relative motion. And that's the mechanical friction we understand. Viscous friction is just another friction. When fluid layer passes over another fluid layer, viscous friction will try to stop the motion. So in all these cases, natural things are happening. In a chemical reaction, say methane is reacting with oxygen, your natural gas in a stove, and burning. What happens actually? There's a difference in fuel and air. There's a chemical difference, big chemical potential difference. And when there's a reaction proceeding, that means it's destroying that potential difference. So we see that signature everywhere. And the second law of thermodynamics is all about it. If you want to say that in language, the second law would be whenever you see difference, nature tries to destroy it. And second law tries to quantify that. Let's see how. And our assertion is that it's through this term called entropy generation. Okay, so to understand that, let's go to this temperature difference, this particular case, and let's really simplify just to illustrate. Suppose only there are two molecules, and so therefore the total entropy means what? In how many ways energy can be stored? And this is at 1000 Kelvin, so we know for 1000 Kelvin these two molecules can have let's say 50 different ways. This one can have 50 different ways, and these guys can have, let's say, 10 different ways and 10 different ways. So the entropy will be proportional to 50 times 50 times 10 times 10s, log of that anyway, but you get the idea, which will be close to 250,000. So this is how many ways in which energy can be stored in this combined system. In the beginning. After a long time, now we still have 4 molecules, but temperature has cooled down, and so each molecule now will have less number of, it will be somewhere between 50 and 10. So let's say it's somewhere 30 ways in which energy can be stored in each molecule. The ladder has 30 steps. So in that case, the energy can be stored in the system in so many ways. which is about, I think it's 810,000. So notice this natural phenomenon that happened shows that entropy of the system is going up. And how can it happen? Entropy is not coming through mass. Entropy is not coming through heat. There is no heating. This is insulated. So entropy must be generated. So this is a process where a temperature difference is being destroyed, and we see that entropy increases as a result. As a matter of fact, it can be shown that in all gradient destroying phenomena, entropy increases. Entropy is generated because of entropy increase if the system is closed, if there is no other ways for entropy to change. How can we remember this? And a simple way to remember this is to just think about friction. As mechanical engineers, we understand friction really well. And friction in thermodynamics should mean that it is trying to destroy velocity gradient. Likewise here, some phenomena is destroying the temperature difference, and that's called heat transfer. So it can be thought of thermal friction that is destroying the temperature difference. Similarly, we can think of chemical friction when there's a chemical reaction. All of these will generate entropy. And to generalize that, we call that thermodynamic friction. So what is thermodynamic friction? What is purpose? It destroys or tries to destroy differences or gradients. That's another term used in thermal fluid sciences. Gradients means rate of spatial change. So any difference in property, when it's getting destroyed, we should immediately understand, gosh, entropy will be generated. So you can have an isolated system. Suppose you have a cup of coffee, you stir it and you enclose it. The energy is not going to change because no energy is coming in or going out. But we know that the motion, if you stir the coffee mug, the motion is eventually coming to stop because of friction. And you can guarantee that even without going into each molecule and counting how many ways, you can bypass all this complexity by knowing that entropy will be generated, by immediately understanding entropy will be generated. Exactly how much? For that, we need the entropy balance equation. You can figure that out from other terms of the equation. So to develop the entropy balance equation, let's go back to an animation. Again, going back to chapter 2. Go to the entropy balance equation. Again, just to remind you, this is the entropy transport we talked about, m dot times s, that a mass can carry entropy. And we also discussed how heat transfer can carry entropy. Q dot over Tk. As you can see, the entropy transfer by heat depends on the boundary temperature. In this case, the boundary temperature is Tk. If the boundary, somebody picks a different boundary, it's called internal boundary. In that case, Q dot, same heat is crossing the boundary. However, the temperature is different, so therefore a different amount of heat will be crossing the boundary, entropy will be crossing the boundary. This is something that we'll explore later on again. Finally, entropy can be generated, as I explained. In this case, the pedal wheel is causing a lot of friction. So the question is, suppose, what do you think about this resistance heater? Electricity is crossing the boundary. We know electricity is not carrying any entropy. However, when the electric heater is getting hot, there will be heat transfer. There is a voltage difference getting destroyed, and there is a heat transfer from the coil to the medium inside, and therefore there is thermal friction, electrical friction. So there is all kinds of reason for entropy to be generated. Finally, to derive the entropy equation, now we have all the ingredients. At time t, we have certain amount of entropy within our red boundary, the boundary of the open system. And in time delta t, we can see that entropy can come in through mass transfer. Entropy can be transported out by mass transfer. And the heat transfer divided by TV, this is the rate of entropy transfer times delta T. This is how much entropy is coming in through heat transfer. And the work transfer doesn't have any impact of entropy. Plus there will be entropy generation, S dot gen times delta T, because of, we know that if there is friction inside the system. For a generic system, we must assume that there may be thermodynamic friction. So at T plus delta T, therefore, we have the final entropy at time T plus delta T is given by original entropy in the system, entropy that came in, entropy that got transported out, entropy that came in through heat transfer, and the entropy that is generated because of friction within the system. So now that we have the complete inventory, we also recognize that entropy can only be generated because of friction. There is no negative friction in nature. If a room is at 30 degrees Celsius, you cannot suddenly come and find that the one side of the room became hotter, another side became colder. That will be considered negative thermodynamic friction. So therefore, S dot gen, entropy generation can never be negative. And that's the second law. Second law means entropy generation rate can be zero at the best or positive. Friction can be absent in an ideal case, but friction can never be negative. That's what second law means. But the entropy balance equation, therefore, reduces to, if I go to the rate equation, we do the same thing we did for the mass and energy equation, change the sides, divide by delta T, take the limit, and what we get is the final entropy balance equation, which states that the rate of change of entropy of a system, the unsteady term of the entropy balance equation, is given by the transport terms, the entropy that is coming in here, going out, minus what is going out there, summed over all the inlets and exits. Entropy that is transferred by heat. We know always heat will carry entropy based on the boundary temperature here. TB is the boundary temperature. Obviously, even though we show just one term, if there are more than different heat transfer, different reservoirs of heat, then we have to split that up into different terms. Q dot 1 by T1 plus Q dot 2 by T2 plus Q dot K by TK, like that. Instead of complicating it with the summation sign, we are just showing it by a single term. And finally, entropy generation term. That is the term that must be greater than or equal to 0, which means entropy there can be friction within the system. And a lot of the time, our goal would be to find that friction. We can do that by finding the other terms in the equation and using the rate equation. So we'll solve a number of problems with using this equation, and the meaning of this equation will become clearer as we solve more problems. So to summarize the rate equation for entropy, we can write that ds dt equals sum of m dot I si minus sum of m dot e sc plus q dot over tb plus s dot gen. Notice the unit for entropy becomes clear now. Q dot is kilowatt, TB is Kelvin. So each term must have the same unit. So therefore, you can figure out the entropy unit. For instance, so m dot must be kg per second. So what becomes of the unit of entropy together must be kilowatt per Kelvin. So the unit of entropy, specific entropy, must be kilowatt per Kelvin, second kg. Kilowatt is kilojoule per kg. Kilojoules per second. Second gets cancelled, so you get kilojoules per kgk. So that's the unit of specific entropy. Specific entropy is entropy per unit mass. As you can see, it's kilojoules per kgk. And the unit of entropy, capital S, is kilojoule per Kelvin. So the rate of change of entropy of a system is given by the rate at which the entropy is transported in, the rate at which the entropy is transported out, plus the rate at which entropy enters the system through heat. Of course, if Q dot is negative, you can see entropy will be leaving the system. It will become a negative term. And entropy that is generated because of friction. So we'll come back again and again to these three equations, mass, energy, and entropy, as we put that together for a special case study of closed steady system next.